Okay, let's dive right into this. Welcome to Gradient Daily. Today, we're unpacking a truly groundbreaking paper from SIGGRAPH 2022 by Thomas Muller and his team at NVIDIA. And look, if you're deeply invested in the intersection of computer vision, computer graphics, and machine learning, you already know the pain. You know that rendering complex 3D environments using neural networks has historically been incredibly, almost prohibitively computationally expensive. But this paper? It's titled Instant Neural Graphics Primitives with a Multi-Resolution Hash Encoding, and it fundamentally shatters that limitation. We are going to deconstruct exactly how they engineered a massive paradigm shift in rendering efficiency and how it opens up entirely new possibilities for real-time, photorealistic visual styles.
Tens of milliseconds. Let that number really anchor our discussion today. Tens of milliseconds. That is the time it takes to render high-quality, high-resolution neural graphics using the architecture we're exploring today. Furthermore, they brought the training time down from hours, or even days, right, to a matter of mere seconds. For a graduate-level audience, you know that optimizing a neural network to parameterize complex visual scenes is historically a massive bottleneck. This leap isn't just some incremental software update. No, it is a complete structural reimagining of how data is stored, retrieved, and processed in a neural architecture. Today, we're going on an under-the-hood reverse engineering journey to understand the exact mathematical and architectural mechanisms that make this staggering speed possible.
So, to thoroughly understand this paper, here is our roadmap for this explainer. First, we'll cover the neural rendering bottleneck. Second, defining neural graphics primitives. Third, multi-resolution hash encoding explained. Fourth, handling hash collisions. Fifth, hardware optimization and CUDA. And finally, the instant real-world results. Let's get started.
Section 1. The Neural Rendering Bottleneck. To truly appreciate the brilliance of what Muller and his team built, we really have to first understand the severe compute limitations of previous rendering architectures.
Now, what's really interesting about this slide is the stark contrast between the traditional approach and this new paradigm. The problem wasn't that previous models couldn't generate beautiful images or intricate visual styles. The problem was the extreme cost of evaluating the math required to actually get there. The old method relied heavily on massive, deep neural networks. Every single time you wanted to query a point in 3D space to determine its color and density, you had to pass that coordinate through a gauntlet of millions of floating point operations. It's just an incredibly bloated and computationally expensive process, severely bottlenecked by extremely slow memory access. The new method flips this entirely on its head. Instead of relying on a massive network to memorize the whole scene, the authors use a very small, lightweight neural network and they augment it with a multi-resolution hash table. This drastically reduces the computational overhead. But to really understand how they pull this off, we need to precisely define our terms.
Section 2. Defining neural graphics primitives. We can't discuss optimization without clearly understanding the mathematical foundation of what we're actually rendering here.
Let's take a minute to deeply define neural graphics primitives. Think of a primitive in traditional computer graphics, right? You've got a polygon, a sphere, a triangle. It's a foundational building block. But a neural graphics primitive, or NGP, is a completely different beast. Instead of explicitly defining a shape with vertices and edges, an NGP is a mathematical model parameterized by a neural network. It acts as the digital DNA for representing shapes, complex light fields, and ultimately the intricate visual style of a scene. Imagine you want to bake an incredibly intricate multi-layered cake. Traditional graphics would be like trying to sculpt that cake perfectly out of hard plastic. You're rigidly defining the surface. A neural graphics primitive, on the other hand, is like having the ultimate dynamic recipe written in a language that an AI understands. When you feed an XYZ coordinate and a viewing angle into this network, it computes the exact color and density of light at that specific microscopic point in space. The neural network's weights act as a compressed, continuous representation of the entire 3D scene. The beauty of NGPs is their ability to represent incredibly complex, photorealistic details without storing gigabytes of raw mesh data. The challenge, however, has always been the immense computational cost of constantly querying that network for every single pixel.
And that brings us to the architecture traditionally used to parameterize these NGPs, fully connected neural networks. In a fully connected layer, mathematically known as a dense layer, every single artificial neuron or node is connected to every single node in the subsequent layer. Let's use an analogy here to picture the problem. Imagine a massive, overly complex corporate bureaucracy. Every time a single piece of paperwork, which in our case is a 3D coordinate, needs to be processed, every single employee in the first department must read it, process it, and individually hand a copy to every single employee in the next department, who then turn around and do the exact same thing. This requires an astronomical number of calculations, specifically matrix multiplications. Every connection represents a weight, and querying a single point requires multiplying the inputs by these weights across millions of connections. When you're trying to render a scene at high resolution with a demanding visual style, you have to query this massive bureaucracy millions of times per frame. The computational cost, the sheer number of floating point operations, becomes an insurmountable wall. It is simply way too slow for real-time applications. The authors of our paper realized they had to bypass this dense bureaucracy entirely.
Let's move to Section 3 and see how this builds into the core innovation, multi-resolution hash encoding explained. We are leaving the massive bureaucracy behind and entering a highly optimized system of data retrieval.
This is the absolute heart of the paper, right here, multi-resolution hash encoding. Instead of forcing a massive neural network to memorize the entire 3D scene in its weights, the authors offload the vast majority of that information into a highly efficient data structure, a hash table. But it's not just one hash table, it's a multi-resolution structure. To grasp this deeply, imagine you're trying to find a very specific paragraph in a massive, multi-story library. The traditional approach is like asking a single librarian to memorize every single word in every single book. Obviously, that's impossible to do quickly. The multi-resolution approach, however, gives a smaller, faster librarian a set of maps, ranging from coarse floor plans all the way down to specific shelves. In this architecture, 3D space is divided into a cascade of grids, from coarse to fine resolution. At the corners of these grid cells, the system stores trainable feature vectors, essentially little packets of mathematical data describing the local geometry, the lighting, and the visual style elements. When you query a point in space, you don't ask the network to calculate everything from scratch. Instead, you quickly look up the surrounding feature vectors across all these different grid resolutions using a hash function. It is a massive shortcut that replaces heavy, grinding computation with incredibly fast memory lookups.
Let's methodically walk through this exact step-by-step architectural pipeline, because this is where the magic really happens. When the system wants to render a pixel, it starts with Step 1, input coordinate mapping. It takes the 3D point in space and locates exactly where it falls within each of the independent multi-scale grids. Then, Step 2 is the multi-resolution hash table lookup. Because a completely dense grid at high resolutions would take up way too much memory, the grid coordinates are hashed, meaning they're compressed into an index pointing to an array of a fixed size. Next, Step 3. Feature vector retrieval. The system fetches the feature vectors from the hash table and rapidly interpolates them based on exactly where the input point sits inside the grid cell, linking these retrieved vectors into one continuous array. Step 4 is where we see the massive efficiency gain. We pass this rich concatenated array of data into a very small neural network. Because the hash table has already done all the heavy lifting of figuring out the spatial context, this neural network can be incredibly tiny. It acts simply to decode the feature vectors into a final color and density value. And finally, Step 5, stochastic gradient descent optimization. During training, backpropagation sends the error signal not just through the small neural network, but all the way back into the hash table itself. Both the network's weights and the feature vectors stored in the hash table are updated simultaneously. Think about that. The model literally learns the optimal spatial map and the optimal decoder at the exact same time.
Moving to Section 4, handling hash collisions. Now, any computer science graduate listening to this immediately recognizes a potential fatal flaw in this system, right? If we are using hash tables to compress infinite 3D space into a fixed size array of memory, we absolutely must acknowledge the mathematical reality of hash collisions. The authors had to solve this, and honestly, their solution is elegant.
Let's explicitly define a hash collision first. A hash function's job is to take an input, like our 3D grid coordinate, and spit out a memory address. But because our high-resolution grids technically have more intersection points than we have allocated memory slots, the hash function will inevitably take two completely different points in 3D space and map them to the exact same memory address. Let's use a highly relatable analogy. Imagine a massive city phone book. You're looking up John Smith. You find the name, but the problem is there are 50 completely different John Smiths living in the city, all sharing the exact same identifier. If you just dial the number, you have no idea if you're calling a plumber or a podiatrist. In our rendering pipeline, if a piece of empty space and a piece of a detailed surface map to the same feature vector in the hash table, the small neural network would receive garbled, conflicting data. It would ruin the visual style and create massive artifacts. Traditional computer science uses complex conflict resolution algorithms like chaining or linear probing to handle this. But those algorithms are slow. They require branching logic, and GPUs absolutely hate branching logic.
So how did the authors fix this without slowing down the pipeline? This is where it gets really clever. The genius lies in the multi-resolution structure itself. It miraculously allows the small neural network to disambiguate these hash collisions naturally without any extra code. Here's how it works.
We aren't just querying one hyper-detailed grid, we are querying multiple grids simultaneously, from coarse to fine. The coarse grids have very few cells, so they don't suffer from hash collisions at all. They provide an uncorrupted, reliable macro view of the spatial context. They know exactly what neighborhood you're in. The fine grids, on the other hand, provide the high-frequency detail needed for a crisp visual style. Yes, the fine grid might have a collision, but the small neural network looks at the data from all the resolutions together. It learns to prioritize the clean, uncollided data from the coarse levels to filter out the noise of the collisions at the fine levels. It learns to ignore the bad data and only pull the high-frequency detail when the coarse context confirms it's looking at the right object. The neural network acts as a perfect, automatic collision resolution filter, keeping the architecture incredibly simple and blisteringly fast.
Section 5. Hardware Optimization and CUDA. Let's pivot from the software architecture to the physical hardware utilization. Because having a brilliant mathematical concept is only half the battle. The true brilliance of this paper lies in its strict, uncompromising alignment with modern GPU design. To achieve training in seconds and rendering in milliseconds, you have to write code that perfectly utilizes the silicon. The authors implemented their entire system using fully fused CUDA kernels. To understand why this matters so much, let's use an analogy. Imagine cooking a highly complex meal. A standard, unfused approach to programming is like chopping onions, putting them in a bowl, carrying the bowl all the way to the fridge, taking out tomatoes, chopping them, putting them in another bowl, carrying that back, and so on. In computing terms, this is executing a small operation, writing the result all the way out to the GPU's main global memory, which is incredibly slow, and then reading it back in for the next step. You waste all your time walking back and forth to the fridge. You are severely memory bandwidth bound. A fully fused CUDA kernel, however, is like a master chef cooking the entire complex meal in a single pot on the stove without ever transferring ingredients between bowls. The authors combine the hash table lookups, the interpolations, and the neural network layers into one massive, continuous program execution. Once the data is pulled into the GPU's ultra-fast on-chip register memory, it never leaves until the final pixel color is calculated. They completely avoid the devastating latency penalty of constantly reading and writing to global VRAM.
So the crucial point is this. Because the hash table lookups for every single pixel are completely independent of one another, the architecture is, as the authors explicitly state, trivial to parallelize. Modern GPUs have thousands of cores designed to execute the same instruction on different pieces of data simultaneously. By using fully fused kernels, they ensure that those thousands of cores are never sitting idle waiting for memory. They are constantly crunching numbers, focusing purely on minimizing wasted bandwidth. Eliminating those memory access operations is the true, hidden secret behind achieving their orders of magnitude speedup.
Finally, Section 6. Instant real-world results. We've spent a lot of time in the deep mathematical and architectural theory. Let's transition to the final analysis section and tie all these dense definitions back to the tangible, groundbreaking results mentioned at the very beginning.
1920 by 1080. High definition. This isn't a theoretical exercise generating tiny blurry thumbnails. The physical reality of all this math, the multi-resolution hash tables, the neural disambiguation, the fully fused CUDA kernels, translates directly into real-time, high-fidelity 3D graphics generation at full HD resolution. The visual style and crispness they maintain is stunning, and they are achieving this in tens of milliseconds per frame. That is the threshold required for interactive frame rates. They have quite literally taken neural rendering from an offline, slow-bake process to a real-time, instantaneous interactive medium.
Let's walk through the numbers here to understand the sheer scale of the achievement and ground it in the specific experiments they actually ran. The authors didn't just test this in a vacuum. They proved it across extremely rigorous datasets. They utilized the classic NeRF synthetic dataset for 3D view synthesis, the gigapixel image dataset for complex 2D coordinate mapping, and signed distance functions, or SDFs, for highly precise 3D surface representations. Across all these datasets, look at the training time. Previous methods required hours, sometimes days, to optimize a single scene. The new hash encoding method drops that to a matter of seconds. A process that used to run overnight now finishes before you can even take a sip of your coffee. For rendering speed, we go from taking whole seconds just to generate a single frame, to generating frames in tens of milliseconds, unlocking 60 frames per second real-time interaction, and finally the network size. We move from a massive, bloated, fully connected bureaucracy to a highly streamlined, small network augmented by rapid hash table lookups. Now, as graduate researchers, we must also critically discuss the limitations of this study. It's not magic. The authors are transparent that memory scaling can become an issue at hyper-extreme resolutions. Because the hash table size dictates the memory footprint, pushing this to, say, 8K or 16K cinematic resolutions could quickly exhaust standard consumer GPU VRAM.
Furthermore, if the chosen hash table size is too small, the sheer volume of hash collisions overcomes the network's ability to filter them, resulting in microblurring or loss of high-frequency detail, which obviously degrades the visual style. As for follow-up experiments and future work, the clear next step is applying this multi-resolution hash encoding to dynamic, moving 4D scenes, essentially pushing this instant rendering into complex video, or utilizing it for real-time generative physics simulations where the environment itself reacts instantaneously.
So, let's consolidate this masterclass into 3 core takeaways that you absolutely need to remember. First, massive neural networks aren't always the answer. Smaller neural networks excel when they are intelligently augmented with multi-resolution hash tables to handle the heavy spatial memorization. Second, the inherent flaw of hash collisions is effortlessly disambiguated because the multi-resolution structure allows the network to use coarse, uncollided grids to logically filter out the noise in the fine grids. And third, mathematical theory must align with physical hardware. By writing fully fused CUDA kernels, the authors bypass severe memory bandwidth bottlenecks, unlocking maximum GPU efficiency and parallelization.
That concludes our deep dive into instant neural graphics primitives with a multi-resolution hash encoding. If this rigorous breakdown helped you grasp the mechanics of this incredible paper, please smash the like button and hit subscribe with the notification bell so you never miss an explainer. Check back tomorrow for another graduate-level deep dive right here on Gradient Daily. And I'll leave you with this final provocative thought. If we can now train and render complex neural 3D environments in mere seconds and milliseconds, how long until every virtual world we interact with is generated entirely in real time by artificial intelligence directly from our imaginations? Think about that. See you tomorrow.